Okay, thank you very much. Yes, so after this short detour, we are going back to quantum computing and just to refer back all the way to this morning where Sophia said that even when we have these fully fledged fault-tolerant quantum computers, we will still run hybrid algorithms on them. And what I will show you today is indeed a hybrid algorithm which is compatible with both near-term quantum computing strategies and also early fault-tolerant or even fault-tolerant quantum computers. And this is a joint work with Tenzan Araki and Balint Kotsor from Oxford. And just to give you a brief outline, first I will formulate the problem, this eigenstate property estimation. Then I will show you what the existing approaches are in both fault-tolerant and near-term quantum computing, and what are their limitations, why do we need new strategies. Then I will introduce some performance guarantees before showing you what the actual quantum algorithm or hybrid algorithm is. And then I will show you a bunch of numerical demonstrations from different areas of physics. Okay, now how does this eigenstate property estimation actually look like? Well, we have as input a Hamiltonian that describes some physical system, and this is the spectral decomposition of this Hamiltonian. So these are the energy eigenstates, okay? And then we also have an observable, and our goal is to estimate the expectation value of that given observable in a target eigenstate of that Hamiltonian psi q. But of course, we don't want to prepare this eigenstate. In some cases, we cannot even do that. And some common assumptions when it comes to solving this problem is that you are given an initial state with this decomposition. And the interesting thing about this initial state is that it has a dominant overlap with the eigenstate of interest. So it doesn't have to be exactly that eigenstate. It usually is not, but it has to have a dominant overlap. And sometimes we also assume that in the spectrum of the Hamiltonian, you always have non-vanishing gaps. So you don't have degenerate eigenstates and those only separated by very, very small gaps. Okay, so this is the setup. And quite a few years ago, the first approach that they come out with that in some form can be used to solve this problem is certain forms of quantum phase estimation, which is a fault-tolerant quantum algorithm. It's a very important quantum algorithm, but it assumes that you have logical, fully fault-tolerant qubits, and you can run very deep circuits on these qubits. So these are some very strong resource requirements that are probably not achievable in the very near future. Now, on the other end of the spectrum, algorithms that can be run even today on today's small and very noisy quantum devices are variational algorithms, which we have heard a lot about today. So you have a variational circuit, and then you optimize the parameters of that circuit. Typically, in a VQE, so variational quantum eigensolver setting, you want to approximately prepare the ground state of that Hamiltonian, and then you can measure the observable that you want. Now, why this looks nice, it also has certain limitations. First of all, it doesn't have any convergence guarantees. So you either get close to that target state or you don't. You cannot really be sure about this. And also what we have heard a lot about today are trainability issues. So barren plateaus, poor local minima, and so on. Now, how to deal with these problems in both settings? Well, of course, you can offload some of the computational burden to a classical computer and first run some parts of your algorithm on a quantum device, then do some classical post-processing, hoping that it can be massively parallelizable, then you can even use GPU clusters to do it, then you're better off. And this general approach is, of course, compatible with both types of techniques. Now to go to a little bit more technical details, I will show you some preliminaries that I will use in the algorithm. First of all, we will prepare an average quantum state, this rho bar, which is basically the Gaussian integral of some time-evolved states. So you take your input state, you time-evolve it for a certain amount of time, and then you integrate it with a Gaussian window. And what we have shown here is that if you calculate this average state, it can be broken up into two parts. First, a diagonal state, so for which the density operator is diagonal in the energy eigenbasis, and then a residual part. This would be an error term in our case. And the interesting thing is that either the trace norm or the Hilbert-Schmidt norm of this error term vanishes super exponentially in the standard deviation of the Gaussian distribution. And this will come in very handy. Now, as the second part of this preliminary section, we rely on this quantum error mitigation technique called virtual distillation, which was introduced simultaneously by Balint Kotsor and the Google Quantum AI team back in 2021. And what they have shown is that if you can estimate this type of nonlinear functionals of your general mixed quantum state rho, so these two objects, then you can estimate the eigenstate properties, so the expectation value of interest, with some error, of course, but this error vanishes exponentially in this number n, which is the number of copies that you have from that mixed state rho. And indeed, you can estimate these functionals with a quantum circuit. If you have these n copies of rho, then you implement some so-called controlled derangement circuit, which basically applies a permutation of these copies. And due to this permutation, certain error terms will cancel out, and you get back this nice behavior of exponentially vanishing error. And now to put these things together, we want to estimate those nonlinear functionals of the time average state. This might not be apparent yet why we would want to do this, but this will become clearer later. But if you can do this, so you can estimate both the numerator and the denominator, then again you get an estimate for your eigenstate property of interest with some error, and that error is basically a function of those two errors which we have seen earlier. One which vanishes exponentially in the number of copies, and another one which vanishes super exponentially in sigma, so the standard deviation of the Gaussian window. And you can see some numerics for this here as well, that if we increase the number of copies, these are equispaced, so you get an exponential suppression, and if you increase sigma, so the standard deviation, then you get a super exponential suppression. And this is for just a trace norm, or the trace distance between this power state and your target state, because basically this upper bounds, with a constant, it upper bounds any expectation value here. So how can you implement this sort of algorithm? Well, you can sample n time values, you plug them into n quantum registers, then you run the same virtual distillation circuit with this so-called Hadamard test, and if you repeat this multiple times and measure, then you get an expectation value which will show this behavior. But we don't want to do this. Instead, we want to estimate these functionals through Monte Carlo integration. So we will have two Monte Carlos, n-dimensional. We basically evaluate n-dimensional integrals where what we integrate are these f and j functions. And as you can see here, we have these a and b objects. And this is where these time average states come in, because due to their structure, they introduce these a and b values, which are basically some overlaps and some matrix elements. And if you have these data from your quantum computer, then you can run all this Monte Carlo estimation in a classical post-processing. So just to look at the workflow of this algorithm, first you define some time grid with cutoff t and time step dt, and then you estimate those A and B objects on these two-dimensional time grids using a quantum device, so some quantum circuits like this with a single quantum register and an ancilla qubit, so this is all that you need. Much shorter circuits than in the case of phase estimation. Then you estimate both of these matrices. Okay, these are of course complex matrices, so you have to run a bit more times. But then you run your Monte Carlo estimators for the numerator and denominator, and then you get your estimate with all those nice performance guarantees by just taking the ratio of these two things. And now to give some hopefully nicer plots, I will show you a bunch of numerical demonstrations. So first of all, let's look at just exact simulation. So we exactly diagonalize the Hamiltonian and exponentiate it to implement time evolution. And for this, we consider a 10-qubit random field Heisenberg model with periodic boundary condition, and just plug in some arbitrary input state, which has 66% overlap with the target state, which is the ground state in this example. And we want to estimate this Z1 observable, so Pauli Z operator on the first qubit in the ground state. And as you can see, these are of course some hyperparameters that we need for the simulation. But as you can see, indeed, with 2, 3, 4, and 5 copies, we get these nice exponentially converging expectation values or vanishing errors. But in each case, we need, of course, more Monte Carlo samples. But okay, this was not very realistic. Let's look at some more something that's closer to reality, which is in the case of early fault-tolerant quantum devices, where the motivation is that it is expected that we will be able to run simple Hamiltonian simulation algorithms such as trotterization or some product formulas. And for this, we consider the Fermi-Hubbard model on a 2x2 lattice, so interacting fermions on a 2x2 lattice with periodic boundary conditions. And this is mapped to an 8-qubit Hamiltonian through Jordan-Wigner transform. And as the input state, we consider the lowest energy state in the 4-spin subspace. And then this has 62% overlap with the ground state. And we want to estimate this Z1, Z2 observable in the ground state. And first, we consider different number of trotter steps. And as you can see, as we increase the number of trotter steps, in each case, which with each of these number of copies, we can basically reach the one that we would get with the exact simulation. And also, you don't necessarily have to run it with all these number of trotter steps. you can just do a few shorter circuits and then extrapolate it to the infinite trotter case, and those results also give pretty nice convergence values. Now, to take one more step closer to reality, we also consider gate noise, which is due to some noisy rotation gates in your circuit. And in this case, we estimate the ground state energy. And basically, we cannot see any difference between noisy and noiseless simulation in either the optimized or the unoptimized quantum circuits, in which case the optimized means that we exploit the fact that the observable, so the Hamiltonian commutes with the Hamiltonian. Therefore, we can significantly simplify the circuit. And now, going to some near-term simulation, we consider this lattice-Schwinger model, which is, I guess, a toy model from high-energy physics or from QCD. And in this case, we run a VQE simulation, but deliberately stop the training at step 50. And then we apply our algorithm with 2, 3, 4, or 5 copies. And as you can see, we can significantly reduce the error of the ground state energy estimate compared to the input state, but even compared to a VQE training, which was run for a longer time. Oh, and of course, here even the time evolution is simulated through variational techniques, so variational real-time evolution on a quantum device. And now, finally, just one more thing, I promise, and then I'm done. I want to show that this algorithm doesn't need to incorporate any quantum part in the case when your quantum system can be simulated with classical methods, so quantum-inspired approaches such as tensor networks. And in this case, we considered a matrix product state, which we time evolved with this TBD algorithm, and then finally those A and B correlators could just be estimated with tensor contractions. And we wanted to estimate both the ground state and one of the excited state energies. And this was for the random field Heisenberg model, but for a 100 qubit or 100 site MPS simulation. And maybe it's not really visible, but this is where the excited state is, and this is where the ground state energy is. And as you can see, with 5 copies, we can basically reach very good precision. But also, if you look at this plot, this is for the ground state energy, then we also see in practice that exponential suppression with these large-scale systems as well. And with this, I want to thank you for your attention.